Go ahead.
Hi. So I'm Alex Sanchez-Stern, and I'm going to be talking about finding the root causes of floating point error using this new tool we built called HerbGrind. Now, numerical software is a really important part of our world. From stock markets to rocket engineering to car engineering, anytime we want to simulate or control the real world, we use floating point numbers to approximate real numbers. So for example, in a piece of software, GROMACS, this thing's a big piece of numerical software that we use for developing medicine and doing other molecular dynamic simulations. And it makes heavy use of floating point. So I'm gonna look at another example here in a little bit more detail. Let's say you've got a complex plotter. This thing takes a complex number and produces, takes a function across complex numbers and produces a nice little colorful graph of its behavior. And when we implement it in floating point, we pass it a continuous function, and what we see is this non-continuous output, where we've got lots of speckling and banding, and things just generally seem pretty jagged. The culprit here is floating point error, meaning that this program is not behaving as it should under the real numbers. Now, a lot of numerical software is really large, written across multiple languages, so it's really hard to track down the cause of such floating point error. We can look at the binary and even go deep down to the instruction that produces the pixel values, that takes a floating point number and produces the color values that we're going to use to display our graph. But that's just a symptom of the error. That's not actually the root cause, and there's nothing we can do to this instruction, or even the instructions right around it, that will help us create a less error-prone program. Now, it turns out that there are actually operations all over this program that induce some amount of rounding, but most of them don't actually matter for the outputs that we care about. And these operations interact in really non-trivial ways. So the root cause of the error that we actually saw is hidden across the operations in this program. So we built a tool called HerbGrind, which takes in a binary program and produces a root cause of any floating point error in that program. And for the rest of this talk, I'm going to talk about how we detect error in the first place, how we see that something has gone wrong in the program, and how we use that to find the root cause of the error, detect the part of the program that would need to be changed to produce a less error-prone program. And the root cause is going to be made up of several pieces of information. We're going to figure out which pieces of code are influencing the outputs we care about. We're going to figure out which sets of operations are working together to create this error. And we're going to report to the user what values in the program actually caused erroneous behavior. So once we've talked about how we develop all these systems, I'm going to talk about running our tool on some big numerical software. And we actually found some important bugs. So but first, let's look at that complex number plotter in a little bit more detail. So here's the function that we were plotting before, and you see the output that we got when we implemented it on floats in the left. If we can figure out the right answer, the one that would have done in the real numbers, then we can compare the two and sort of start quantifying what the error is. We can produce some piece of information that says that when we hit the pixel value conversion routine, we saw that 88% of the pixels we got were wrong. But this is just a symptom of the error. It's not the actual piece of the program that you would need to change to get less error. And finding the root cause of the floating point error is really hard for several reasons. Floating point error is non-compositional, meaning that local accuracy doesn't necessarily lead to global accuracy. It's non-local, meaning that the causes of error can be spread across the program. And it's non-uniform, meaning that the error you see depends highly on the inputs you give it. So I'm going to talk about these three things in a little bit more detail. And to explain what I mean by non-compositionality, I'm going to go through an example here. Let's say you've got a program over the real numbers, and it's just x plus 1 minus x. We should always compute 1. It's a pretty simple program. And we implement this in floating point. Now, if we pass both the real number version and the floating point version the same input value, 10 to the 16, we'll see that their executions actually start to diverge a little bit. So they both try and do the same thing. They add 1 to 10 to the 16 and then subtract 10 to the 16. But the floating point version, when it adds 1 to 10 to the 16, is actually going to create some rounding. And this is actually a pretty small amount of error compared to the values we're looking at. 10 to the 16 plus 1 is not even representable in floating point. So we've still produced like the closest floating point number to the one we want. But then when we do the subtraction, we'll find that we get 0 instead of 1, which is a completely wrong answer. So even though we had 2 operations, one of which was pretty accurate, almost entirely accurate, and the other which was completely accurate, together when they compose, we get a lot of floating point error. Now, in this example, the operations that we care about are right next to each other. So you can imagine a programmer looking at this and figuring out that there's a problem. But in general, this isn't true. Floating point error can be non-local, meaning it can be spread out across the program. So in a very similar example here, we've also got an addition and a subtraction that could cause this kind of error. But they're in 2 separate functions. And the values that we care about are actually flowing through data structures. So you can see the floating point behavior that causes the error can be spread both across space and time in your program. Finally, floating point error is non-uniform, meaning that the error we get depends a lot on the inputs we give it. So for this program, almost any value of x will produce a perfectly accurate output. But if you give it a value of x that's near 42, we'll see a lot of floating point error. So because of these things, it's really hard to track down root causes. But what is the root cause of that complex plotter we looked at earlier? You can see that we have the bad output on the left, but the steps involved to producing this output are quite complicated. In this case, actually computing the complex function that the user provided this complex plotter is where we go wrong. Because that complex function involves some complex square roots. And when we implemented those in the plotter, we used this formula that you'll find in a lot of math textbooks on Wikipedia for a complex square root. And it turns out that implementing this formula as you see it in floating point actually causes some inaccuracy. Because when x is pretty large and y is pretty small, the term on the right here is really inaccurate. And you get a similar behavior when x is really large but negative and y is small on the left. So the tool we built, HerbGrind, is a root cause analysis tool. So let's see what happens when we run it on this complex plotter. We'll get the detailed symptom like before, but we'll also get the root cause information, which is the information that you would need to fix this floating point error. Here we'll see that that we have the complex square root routine, which is just called square root complex here, and that expression that we showed on the left is the culprit. So I'm going to walk through each of these. Oh yeah, and fixing this produces a better program. I'm going to walk through each of these pieces and talk about how we find this information and provide it to the user so that they can fix the floating point behavior in their code. So the first thing we need to do is figure out how much error there was in the first place. And to do that, we need to know what the output should have been. So our analysis will look over the binary program, and for every floating point instruction, it's going to watch what it does on the floats, but it's also going to shadow this floating point execution with a real execution. Now, we use super high precision floats for this, but there are a few different representations we could be using, and we're sort of orthogonal to that. But what happens if instead of just a single routine, the program involves some call into a math library because it wants to use arctangent or exponentiation? Now, these math libraries, when they implement these kind of routines, don't actually do so in a way that makes sense on the real numbers. They'll often do it with like precision-specific bit operations. So if we just try and shadow these operations, we're going to get the wrong answer. Instead, what we'll do is we'll recognize these kinds of calls and intercept them and shadow them with their high-level equivalents. So we'll just run a high-precision ATAN when we see this operation. So once we can do that, we can actually run the entire program on the reals and compute what the right answer is. This is much slower than actually running on the floats, so it's not useful in practice, like in your production software. But to find the root cause of floating point error, it's very useful. But just figuring out what the right answer is and how much error there is isn't enough to fix the problem. We need the root cause information. So the first thing we're going to do is figure out which pieces of code that could potentially be the root cause are affecting the output that we care about. Now, how do we figure out what could potentially be a root cause of floating point error? It turns out we'll recognize these things called error amplifiers, which when we see them, we know there's a root cause somewhere nearby involving an error amplifying operation. So like I said before, there's lots of operations in your program that are going to round. So we can take our real execution and we can look at any operation and we can round its output, and we'll see that we get some amount of error. But an error amplifying operation is one where if we round its inputs, we'll actually see a much larger amount of error. So that's how we figure out that an operation is an error amplifier. When we see error amplifiers, we need to know if they're affecting the outputs that we care about. So what we'll do is we'll attach a reference to that error amplifier to the shadow value as we propagate through the program whenever we see this error amplifier. And when we build new values out of old values, we'll propagate the information about what error amplifiers they hit. So that whenever we hit an output of our program, we can look at the value that got to that output and figure out what pieces of problematic floating point code actually influence that output. But just seeing the one operation isn't enough, because floating point error is non-compositional. Each operation is accurate, but the composition of them can be inaccurate. So we need to know what operations work together to create this problematic floating point code. So to do that, we're going to build these symbolic expressions, which will tell the programmer what are the operations that cause this problem. So we're going to do this in a very similar way to before. We're going to build up these values that ride alongside the actual values in the program and follow them as they compute. Whenever we see an input, we'll just make it a constant or a variable. And when we build new values out of old values, we'll also build these symbolic expressions out of the arguments. It's actually a little bit more complicated than this to get fully general expressions, but we'll go over that in the paper. Finally, even if you have the code that produced this problem, you still need to know what inputs cause problematic behavior, because often, for most inputs, something's perfectly accurate. So to get this information, we're going to take our expression and break it down into a tree. And at the leaves of the tree, we'll hold information about what are the inputs that came into this expression. And every time this expression executes, we'll propagate the information about the inputs up to the top of the tree. And if we see local error, we'll remember that for these values of x and y, we had problematic behavior. So we'll do this for every value of x and y that goes through this expression. But if it doesn't produce error, then we'll just throw it away. And if it does, we'll add it to this set. So at the end of the program, we know exactly which values of x and y caused error. So with these pieces of information, we have everything that we need to track down the root causes of floating point error, at least in theory. However, in practice, there's still a little bit more we need to do. The first thing we want to do is scale to really large programs. Now, the analysis that I've described so far, implemented naively, is still too slow to scale to the large numerical simulations that we want to deal with. So to allow it to scale, we used a few different tricks. We built a static type analysis, which can look over the binary code and figure out which values couldn't possibly be affecting floating point behavior so that we don't have to watch them. We'll bound the size of the trees we collect so we don't end up updating trees that are thousands of nodes deep. And we'll incrementalize our analysis so we only hold as much information as we need as we move along. Next, we'll find that in real-world code, a lot of the abstractions we rely on get broken. So we already talked about the way that math libraries use bit tricks to implement these high-level operations. Compilers actually also do bit tricks that they'll compile straight inline into your program. But when these things are done inline, we can pretty easily recognize them and do the right thing. Finally, when experts write numerical software, they often use tricks in the writing that don't really make sense over the real numbers. So they break a little bit of our abstractions. So for instance, experts will often build up error in one part of the program so that it can cancel out error in another part. And if we just treated this naively, we would look at these places where error is built up and we would report them as potential root causes of error. And we'd have a lot of false positives. So instead what we're going to do is we're going to try and detect where experts are using these tricks and not report the false positives. The way we'll detect this is by looking at operations where one of the arguments has the same real value as the result of the operation. But the result of the operation has a lot less error than the input. We'll know when we see these operations that it was a compensating operation where error was used in one place to cancel out error in another. So the error that was intentionally built up, we'll ignore as potential root causes. So once we have all these things, we're actually ready to run on real-world software. So we ran on some real-world software, including this big piece of software, Triangle, which actually won some awards for well-written numerical software. So we wanted to use it to test our handling of expert numerical tricks. If we turn off our handling of expert numerical tricks, HerbGrind actually produces 255 potential root causes, which we know is not quite right. And we investigated these manually and found that actually the program was doing the right thing. When we turn on our handling of expert numerical tricks, 95% of those false positives go away. So we found the system's actually really effective. Finally, we also ran on this big piece of software that I talked about in the introduction, which does molecular dynamics and is used in medicine and biology. And it's a huge piece of software developed over decades and written in multiple languages. So we knew it would be a good stress test of our ability to scale to large software. Now, we still have a bunch of overhead on this kind of software, but we got it low enough with the systems I talked about earlier so that we could actually run on the test data sets and start finding the root causes of error. And when we ran on GROMACS, we actually did find a bug. It turns out that in the dihedral angle routine, which is a function that computes the angle between two planes, when the planes are really close together, GROMACS was producing an angle or a computation with a lot of error. And while this is a pretty small set of all the possible values that this function could take on, it's actually pretty common in practice. Because whenever you have 4 atoms that are bonded collinearly, we're going to be computing these planes that are really close together, and we're going to get a lot of numerical error. So using the root cause produced by HerbGrind, we were able to fix this bug, and the fix was confirmed by the developers. Obviously, HerbGrind doesn't stand alone in the space of floating point tooling. There's a lot of amazing work out there for synthesis of numerical snippets and verification. So we've got this work DAISY from MPI that was used to, or is used to verify and synthesize numerical code. There's also some other work, Salsa and Herbie, that is just there for synthesizing better numerical code. And this other piece of work, FPDebug, that does a similar real shadowing to detect potential sources of catastrophic cancellation. In the future, we'd like to make our analysis even better to scale to larger scale programs. And we'd like to build new analyses using the infrastructure that we built here. Finally, we one day dream of having a fully automated floating point repair pipeline where we can work with some of the other floating point tooling in this space. We can have HerbGrind extract a root cause, have DAISY or Herbie produce a better way to compute that function, and then finally automatically reinsert the better code into the binary or source so that without any manual work by the user, we can fix floating point behavior. So thanks for listening. I hope you download our tool. It's available online. It's free and open source. And I'm happy to take any questions.
Hello, thanks for the talk. I'd like to know how you handle potential control flow divergences. For instance, in this case of symbolic representation of causes, what happens if it's not only a problem of round-off error, but the fact that there's a control flow divergence and the instruction that is executed with floating point is different than the one which would be ideally executed?
So we wanted to be really conservative about control flow divergences that could result from floating point behavior. So what we do is whenever we see a control flow change based on a floating point value, anytime we do some like comparison and then branch on it, we're going to mark that as an output of the program so that we report any sources of error which could have potentially affected that branch.
Okay, thanks.
I actually had a couple of questions. When you talk about error amplifiers, you're talking about operations that greatly increase the relative error in the value. Okay. The other question I had, and this is sort of in response to the last question, you said you consider any sort of control flow changes substantial, but what about something like an absolute value function, which is actually continuous? And where a small change in the input might affect the branch that you take, but won't affect the output very much.
So because we wanted to be conservative, we're not going to be able to detect if it didn't affect the output in a way that the user cares about. But what we are going to do is report exactly how many times the branch went wrong and the values that caused the branch to go wrong. So the user can look at that report and determine for themselves whether it's relevant or not.
I wanted to ask that what is the guarantee that the root cause determined by the tool is correct?
Well, we don't have any sort of soundness proofs or guarantees because we're doing a dynamic analysis that depends on the inputs the user is going to give us to the top level program.
Thank you.
Any other questions? Thank you very much.